We are given three derivatives to evaluate. The first one is the derivative of a quotient. Let's write down the general formula that we will use. We have a quotient of two functions of x, and let's write it down in Newton's notation over here. G of x squared in the denominator, and here is our numerator. So we have the differentiated numerator times the denominator minus the numerator times the differentiated denominator. In our case, f of x is equal to ln of x and g of x is equal to x squared. So f differentiated of x is equal to 1 over x and g differentiated of x is equal to 2x. Now we'll use this formula to solve our first problem. We plug in the calculated values. We have x to the power of 4 over here. We have 1 over x times x squared minus ln of x times 2x. So this is x minus 2x times ln of x over x to the power of 4. We can extract x and now we can cancel out this x with x to the power of 4, which leaves power of 3 in the denominator. So the result is 1 minus 2 times ln of x over x to the power of 3. In part B, we have a derivative of a composition of a function. We'll start by differentiating the outer function, 1 over 2 times square root of 3 times sine square of u plus 2, and then we need to multiply this by the derivative of the function inside within the square root, 3 sine squared u plus 2. Once again, we treat this as a composite function. Actually, we first treat it as a sum of two functions, but the derivative of the second function is 0, so we can just concentrate on the first one, 3 times sine squared of u. 3 goes outside. When we differentiate sine square of u, first we obtain 2 times sine of u, and then what's left is to differentiate sine of u. Here these two and these two can cancel out. When we differentiate sine u, we obtain cosine of u. Sorry, plus 2 must be over here under the square root. So we get 3 times sine u times cosine u, which is obtained as a derivative of sine u. And here below we have this squared root of 3 times sine square u plus 2. Finally, we have the nth derivative of e to the power of k times x, where k is constant and x is equal to 0. Well, we can do the differentiation gradually. Here we have n minus 1 derivative of the first derivative of e to k times x. And all of that will be evaluated at x is equal to 0. We copy this part. And here, when we differentiate e to the power of k times x, we obtain k times a to the power of k times x. It is already obvious that each derivative will extract the factor of k, and e to the power of k times x will also remain. So after we perform n derivatives total, we will have k to the power of n times e to the power of k times x evaluated at x is equal to 0. E to the power of k times x, where x is equal to 0, is equal to 1, so the final result is k to the power of n.